Well, welcome to NeuroNoodle's Neurofeedback and Neuropsychology podcast featuring our neuropsychologists, Dr. Laura Jansons, Dr. Skip Hrin, and neurofeedback legend Jay Gunkelman. Our goal is to promote options for better mental health. Specifically, we focus on the objective data you can receive from a brain map and the positive results of training with neurofeedback. Occasionally, we'll bring on guests who have a different modality. Got to have an open mind, right? This is an all-star cast and are more than happy to share their knowledge with you. Please give us 5 stars on Apple Podcasts and subscribe to our YouTube channel. You get to see some of the behind-the-scenes action. We don't always sound this smart as we do on the Apple Podcasts. Speaking of Apple Podcasts, it really helps if you could give us a 5-star rating. It helps get the word out, spread the positive vibe out there, because if they can't hear us, we can't help them. If you're not a subscriber, visit neuronoodle.com to sign up for our newsletter. We send out a weekly update. My name is Pete, and today we have on the show Tomas Ros, Ph.D. cognitive neuroscientist and author of many academic studies. Dr. Tomas, thanks for coming on the show today.
Pleasure. Thank you for the invitation.
Now, Jay mentioned that we should get you on the show, and of course, we always do what Jay says. How do you two know each other? I know everybody knows Jay, but how did you connect?
I believe we connected at the ISNR conference circuit, right? Very back in the days. I think I must have started neurofeedback at 2005-06, and I think maybe the first conference that was in Europe was it's in SAN, right, in Swansea. But maybe we met even before that. I can't remember exactly the timing.
Well, it's for me, it all blends together. So I'm not really good on serializing the past. So picking precise times is difficult. But Swansea was definitely one. I remember your association with John Gruzelier, who's been an old friend of mine for a long, long time. In fact, you've probably been in his office, so you may actually have seen the picture, which he hung on the wall in his office, I understand. He was over at an AAPB meeting, and they have a badge, and they stick little banners beneath the badge, and some of them have a very long bib of these badges, hanging down over their bellies sometimes. And the longer you've been in the meeting and the more things you do, the more of these little things you get. And he thought that was the funniest thing he'd ever seen. So, and I was on the board at the time, so I thought, well, we might as well have some fun with this. And I went up to the front desk, and behind the desk, they have all these badges all in bins. And I just grabbed handfuls of various ones. It didn't make any sense. 50-year member, first time attendee, it didn't make any sense. But we made them a very, very, very long, we were calling them a bib, but John called them a codpiece because they became so long. And so he and, oh goodness, I can't remember which one of his students was standing there next to them. They had these big long bibs, and he thought that was the funniest thing, and he placed that on the wall in his office at one point. So, silliness.
We know each other from I was his PhD student at the time, so that's basically how we know each other. And I came to the US multiple times after that for the other ISNR meetings. I also gave a keynote at the ISNR once a few years back. I don't know. Are you still going there, Jay?
I don't get out anymore at all. I'm not well enough to attend face to face. Well, nothing's been going on face to face for a couple of years anyway. And I have a cerebrospinal fluid leak, so it's not safe for me to be out and about. But the meetings were a crossroads where we met many, many folks. Your work with Gruzelier bridged a whole bunch of different topics, from training surgeons to have better performance, to athletes and performance, to elite musicians and their performance, and then ICA connectivity work and so forth. So you cut your teeth for probably a good decade there with John.
Yeah.
But your more recent work on PTSD, I think, was also quite interesting. You ended up intersecting with Ruth and her work.
Mm-hmm.
So,
I started through the kind of the artistic or more peak performance back door. So John was interested in work on like enhancing performance in general, in this sort of general population as well, like who are some kind of experts like surgeons or musicians and artists and so on, and actors and so on. And this was based on this alpha theta work that, found that there was kind of increase in creativity maybe that could help. Although I would expect that, in surgeons, you don't really want them to be too creative. But
because of the script, right?
But we didn't find that, fortunately. We find that the SMR protocol was more beneficial in the surgeons. But essentially, I sort of, the long story is that I sort of, the short story actually is that I saw John giving a lecture in London after I finished my master's in France. And I came back to London to do my PhD, and I was looking for a PhD position, working with neuroscience, because I did a master's in neuroscience. And there were some, positions, but it was difficult to get actually a PhD. I made it to a few interviews, and then somebody else took the job. And basically, I was wondering around, like, okay, what am I going to do? What am I going to do next in my science career if it's going to happen at all? And then I stumbled on a lecture kind of saying, okay, John Gruzelier speaking about peak performance in music and creativity. And I was like, I'm really interested in music and the mind. So I went for this talk, and I saw John, and then I was like, I need to speak to him because I really would love to do a PhD in his lab. And essentially I approached him after the conference saying, look, I'm looking for a PhD. Do you have maybe some kind of a project for me? Like I could even start for free, At that time it was like, just get your foot in the door. He did say, yes, come to my office and, we'll talk about it. And at that point, there was this surgeon study that I think one of the PhD students that he was working with at that time stopped, sort of left the PhD midway. And then basically he gave it on to me, like, complete confidence that I was going to do this right. Well, I had no experience with EEG whatsoever. So I was kind of thrown in the deep end, but it was an interesting one where we basically had a little neurofeedback room inside the hospital, inside the eye surgeon hospital. And I was kind of resident there every day. And I saw surgeons, for lunchtime doing neurofeedback. And they used to call it TT with Thomas, which was like torture with Thomas. It was like they had to do neurofeedback on top of all their surgeries. They never got any sleep. So probably, they actually ended up sleeping during most of the time. So that's the backstory of that study. Anyway, it was a good time, and also these ISNR meetings were kind of the only ones that kept the neurofeedback field alive, in my opinion, at least academically as well. So I was happy to meet the community, and we met. Also, Barry Sturman came to Swansea, and also I met the late Joe Kamiya that I heard just recently passed away. So I would like to dedicate this podcast to him, to the founder of the field that I think nobody outside the neurofeedback really appreciates how much his discoveries, basically created this field out of nothing.
I totally agree with the dedication. We've lost many major figures, and Joe Kamiya being one of the the foundational figure, actually. And he, in 2012, Joe gave a talk in Europe, and he did a slide of Barry's cats, and a quote from Barry that if brain activity was behavior, we should be able to train it, and but it all goes back to Joe's work stemming to the 1950s, and to a certain extent his life experience, which was not really always favorable. I mean, he was a minority in the Central Valley before Asians could own land, and they were field workers, and World War II came and they were in an internment camp, which he says wasn't so bad because he didn't have to do field work. And he got to play baseball with the kids and whatnot, but it gave him time for introspection. And I think a lot of his focus on internal states may have been spawned from some of that time spent, introspection. But nevertheless, he ended up working in Kleitman's lab with Dement and Kleitman on identifying the internal state associated with dreaming and the convergent evidence of subjective report and objective measurement of the REM state. And then he tried to expand that to making some kind of a identification of what this alpha rhythm was about, and showed that it could be identified with discrimination training in the 1950s. So it all stemmed from his work, and it's a huge loss. And I was having some difficulty with it, actually. I'm, not without 48 years of knowing Joe, but it's people like yourself that have the bright future for the field that kind of keeps me from just being totally bummed out. So thank you.
Yeah. Well, it's an honor to continue the legacy. And, as in many other domains, there's always the passing of the baton. So, that's the whole point, is like somebody makes some seminal discoveries and we work on top of the shoulders of giants. And I think, there's this whole area is really unexplored. I mean, I think it was just opened up, and then now let's see what science can do. I believe in the scientific process, ultimately, although it's a love-hate relationship in some ways, because this field really hasn't taken off for very many years, and there's been a hibernation, due to many factors. And, we could have long philosophical discussions about why neurofeedback has taken so long to be investigated scientifically, or the funding has been very weak as well. And even my own career, without trying to complain too much, it's been a rough ride. So I hope we're now at a point where, the new generations, and I consider myself now maybe even part of the older generation. You can see my gray hairs here, but everything is relative. But there's many more new scientists who come to this with a fresh set of eyes, a fresh set of ideas. Let's say they're not burdened by the past and burdened by other approaches that I think have maybe reached their limits, to some cases, and we need innovation. And as much as science likes to claim that it's innovative, I think it's almost the opposite. We always keep hitting the same nail on the head, whether it's like pharma sector is always trying to promote new drugs and the same approach 1,000 times when we know that it has certain limitations. So I'm very surprised this hasn't been already tested way back. And I think there's a few papers that came out back in the 60s and 70s that Joe and Barry Sturman have published, and you could think that they would have been, they broke the glass ceiling where they got their papers into like famous journals like Science, but nothing. It sort of fizzled out, and then I think from what I heard, the stories were that there was not enough funding, and even though they applied for NIH grants, nothing happened. So I think that's really the key, that if you don't have scientific funding, then what can you do? Like, well, you're not going to be able to do it yourself. But it's great that this field has survived, let's say, underground, or at least on the surface, to keep going until other figures maybe got the funding, or like you drop out of the race, somebody else comes in. I was worried that I was going to drop out of the race a few times. Frankly, I was, to be honest with you, I was on unemployment for a few years because I didn't get the funding. And then I was just saying, well, what do we do? Like, do I just exit science? Because, and I put all my eggs in this basket. And I did that on purpose because I knew that, nowadays you have to specialize, and I also believed in it. I've seen effects myself. So I really truly believe that neurofeedback could do something revolutionary. but it requires the evidence base, and to get the evidence base, you need funding. So, even though from the studies that we've done, I could still say that maybe interest is a bit weak compared to other domains, right? So we got into some good journals and so on, but as I said, even Joe and Barry got into good journals and to no avail. So it's more about the collective mindset that I think the trajectory of human consciousness is on, in terms of like, okay, we've exhausted one paradigm, here comes the next one. And hopefully we've got to that point now that we can try other technologies and maybe even the whole BCI, consumer grade devices, everything going digital, digital health, all those things are feeding into this whole confluence of neurofeedback maybe being the next paradigm that finally science will investigate.
Thomas, that's why we have this podcast going, to get the word out. I mean, it's our way of trying to get more people together, because it seems like Jay brought it up. It's like a circular firing squad. Everybody's operating in their own silo, and hopefully we can get more people together.
Yeah.
You had an article. You were quoted in an article not too long ago in the Tech Explorist on ADHD.
Mm-hmm.
I want to say Pranjal Mehar, of course I'm saying that wrong, but it addressed ADHD. And, one of the things that at least I know as a layman of the group, that the efficacy for ADHD and neurofeedback is at the top. Do you want to talk about, I'll throw this out there and then Skip, you can take over, how neurofeedback can help in the studies that you've seen or even done, because you have so many publications out there. Because we have parents listening to this show, we have end users, we have technicians, we have clinicians, and if we can do anything to get the word out there, maybe everybody's all the kids are getting diagnosed with ADHD. How can neurofeedback help with ADHD? I'll hang up and I'll listen for my answer.
Should I go first?
Yeah. Hit it.
Well, as a scientist, I cannot be sort of too publicizing about certain approaches, because I need to take a sort of impartial and evidence-based approach, right? So that's the scientific side. Then there's my human side, which is about, okay, what are the other options, right? And we know, okay, so although neurofeedback has been the most successful in ADHD, I would say, or at least most number of studies on it, you have to consider that even though psychotropic drugs don't necessarily work very well, methylphenidate, the main sort of treatment for ADHD, is atop of the list of the most successful pharmaceutical drugs for brain disorders. So it has an effect size of around 1, which is hard to beat, I have to say. So you have to show the gold standard that this can be replaced with something else that has some other benefits. In case of neurofeedback, that doesn't have side effects, and it can have even maybe be a cure, because once you stop neurofeedback, you shouldn't necessarily have to keep doing it, whereas you have to take medication all the time. So that's kind of the reference point, that we kind of match at least, neurofeedback matches at least the effect size of methylphenidate. Now, recently we did a study with theta beta neurofeedback, sort of the older protocol, and we found that wasn't necessarily the case, that even though neurofeedback had an effect size of around 0.5, which is still pretty good, it didn't sort of displace, let's say, methylphenidate. So we have to keep, let's say, looking for maybe potentially more specific markers of ADHD, knowing also that ADHD is not just just a term that one uses behaviorally. That's clear, but also that it has many different sort of signatures neurally, right? So there's different subtypes and so on. And we know more and more we're grappling with this kind of heterogeneity, this kind of diversity of even within a particular disorder, different patterns that different people present, different children present. So it's not a static thing that you can just kind of lock onto and shoot the rocket at, but it's more like different flavors of the same problem, but different nuances, different dimensions. Some have more hyperactivity, some have more inattention. Then, neurally that's expressed by different patterns of the brainwaves, like some might have more theta and so on. So you need a more tailored approach, let's say. So that's, I think, the harder part is like, how do we boost the efficacy? So I think the efficacy is there, at least an effect size of 0.5, which is considered, medium to large. But if we want to really displace the sort of most successful pharmaceutical drug for brain disorders, we need to explore more and get more specific in terms of the protocols. That's my summary. But I would say that it definitely has a future, conceptually it has been demonstrated to work, especially for those types that, for example, when the protocol does fit the phenotype, where let's say high theta beta ratio is shown that it correlates with the efficacy of the neurofeedback protocol. So for those that have a high theta beta ratio, then neurofeedback seems to be effective. That's, for example, the studies by Gevensleben and al. And Heinrich's group. For those that don't demonstrate that, let's say, abnormality, you might need some other protocols that are more specific and more applicable to that signature, right? And maybe even looking at other markers, so going beyond simple power-based measures, based on sort of oscillatory power, but like maybe connectivity might be a more specific marker of the problem. So we're only going to we're only getting into that sort of complexity as technology improves and signal processing improves as well. Yeah.
That's the difficulty with an experiment. It's easy to set up an experiment, but having one that customizes the treatment to the patient ends up being very difficult to end up constructing. You're absolutely correct. There's multiple phenotypes or clusters of ADD types, and the training has to match their type, otherwise you don't get the proper outcome. And the difficulty at this point in clinical work is that the clinicians have so many treatment options, and not all of them end up having literature support at this point. Some of them do. Usually the older, simpler protocols end up having at least some literature support. But unfortunately, the field progresses without necessarily all of the scientifically published support that it would hopefully have. But I started in the field in 1972, where there wasn't any scientific literature support for anything other than training alpha, basically, or training SMR. And I had a clinical laboratory. We actually wrote a grant in 1974 for alpha training in alcoholics. It wasn't funded. The government quit funding in the 70s. But, we could see positive clinical outcomes. I was excited about the field back then in the early 70s, and I'm even more excited about it now. At this point, there's actually a fairly solid scientific literature.
Yeah, and there's a lot of different patterns that are found to be associated with ADHD, and some of them are contradictory, like at first sight. You might find you have, like in children, you have lower beta power in ADHD, but there's also the higher beta power. So how can both be related to ADHD, right? It doesn't make sense. But in fact, it might make sense from the point of view of an inverse Q curve, where you have sort of optimal level, like an intermediate level of power, or the way that, some of the brains are tuned to be in a kind of a sweet spot. And then any deviation from that sweet spot, whether it's high or low, creates, dysfunction, cognitive dysfunction. So these are models that haven't yet been necessarily absorbed by the neuroscience community. A lot of people still think up and down, and high is good or low is bad, and so on. And essentially, we need to revise also. We have to get a better idea of how the brain functions, how brain activity is related to optimal function. And from there, then, develop neurofeedback protocols based on those tools. And I think, interestingly, like neurofeedback has sort of, developed in the same sort of dynamic as QEEG. They kind of go hand in hand. You have the QEEG and the neurofeedback. And both of those, I think, are seminal, fields, even on their own right, because just now, recently, people have started looking at, quantitative EEG as something that you could classify different symptoms or a new machine learning. And, this was being already done a long time ago by Eur J and Robert Thatcher and so on. And, comparing your brain to a normative database where you're looking at these kind of Z-score deviations or differences, whether it doesn't matter whether they're high or low, but it's a kind of the deviation that's important. And, new models of psychiatric disease exactly point to that. So now, people and publications are being reported in very nice journals, good journals about normative modeling. And, you never see Eur J being cited in those journals, right? In those papers. And on Twitter, I kind of highlighted it. I said, you think you're inventing this thing, but actually somebody else invented this before you, but you just didn't read literature because you're stuck in fMRI. But if you look at the EEG, they already came up with these concepts a long time ago. But this is a kind of a little bit also reinventing the wheel in some ways, because as the new generations come, they think, oh yeah, we're going to promote this as a new thing. And, to get their papers published, they need to make it look novel. So whether it's unwittingly or wittingly that they don't report previous, fields or previous approaches, it's kind of sad that happens. So I would say that, both in the fact that neurofeedback, people are finally doing neurofeedback, that's vindication that was the right way to do things, or at least to investigate this area, which was really badly funded. And the fact that QEEG also, normative modeling, is coming back into the fray, again, as a vindication of, you could say maybe even fields that are outside of science to begin with, and then suddenly, well, voila, we're back to the starting point. So it's ironic, really.
Thomas, I know you have mentioned the paradigm shift, and geographically we're in different spots. So I wanted to ask you about that in just a second here. But over in the States, how we come about with ADHD diagnoses predominantly is through the use of the DSM, which is a pretty vulnerable punching bag that we try to work out on this show as much as we can, because it's based on observable symptoms, right? And so our paradigm, despite what we're trying to accomplish on this show, and the folks that listen to it and everybody that's in the choir, so to speak, would prefer maybe if we came from a neurological basis of generation of behaviors versus just what we see, right? Mm-hmm. And so we struggle, I think, with that being the predominant way to get to a diagnosis. And so we're coming at it, it seems like, when we meet with people that aren't in the neurofeedback world or even neuroscience world, that we're talking about things that just are unfamiliar, and it's almost a different language of sorts, right? So all that to ask you this, and Jay, please jump in too, but what's the climate like where you are? You've already referred to a paradigm shift and maybe different ways of approaching behaviors. Like, hey, it's not just that you're having trouble sitting still, so you have ADHD. It's like, hey, let's see what's going on and what's contributing to you having difficulty sitting still, maybe through EEG or other ways of monitoring or visualizing this activity. Can you speak to that?
Sure. I mean, that's the overall kind of dream of cognitive neuroscience and neuropsychiatry in some ways, is to kind of try to explain these behavioral differences with some neural, underpinnings. Now, it's easier said than done, right? And so far, it's actually used by a lot of groups as a sort of a null finding, that in fact, we haven't found anything really reliable using all these fancy methods, right? Neuroimaging and all, even animal models and so on. And that since let's say the predictive power of using neural markers for DSM disorders is, verging on 60, 70, maybe basic 70%, not higher than that, I would say in most cases, that they're kind of worthless and that we should give up on the whole biomedical model. Now, I'm kind of understand both sides. I don't think that you can explain everything with biology, although the brain does generate behavior. So, by definition, we should be able to find it. Now, the causes is a different matter, whether, the brain disorder causes are genetic or environmental. I think they're probably a combination of both. But that argument, I think, is less interesting. What's more interesting is can we find more specific markers? And okay, the current markers we have, like say P300 for ADHD, it's not bad, and it can maybe help diagnosis, but at the moment it can only do so as an auxiliary, so sort of adjunctive thing where it can maybe inform diagnosis, but it cannot be the whole thing because it can only explain 70% of the variance, right? Then you also have to question, okay, do the psychiatrists also, diagnose disorders just like that, willy-nilly, right? Not necessarily completely logically, right? Because they just tick some questionnaires, although usually they're cutoff values. But famously, they've done a study where they tried to do machine learning on just basically the questionnaire sort of values, and they couldn't really get to the same classification rates that, and also inter-rater variability between psychiatrists can vary based on diagnosis as well. So diagnosis is not a hard fact. It's quite variable also between doctors. So I think we're in both domains, whether behavioral or neural, there is a lot of it's still a bit fuzzy. And although the doctors, they claim the upper ground because they're, elected to make those diagnoses, they still have the sort of the final say on, who has or doesn't have ADHD. But I think hopefully with more technology or more advanced signal processing, we might find some of these, signatures that could be more specific to the behavior. But I think for that to happen, we also need to have a science of behavior that is, let's say, more specific as well. Because at the moment, we do questionnaires, and some of these tests are also a bit simple, like computerized tests, like TOVA and so on. They just look at one dimension. So we need to expand this behavioral, sampling or behavioral batteries to be more specific, or let's say have multiple dimensions that we can then kind of gauge. And then from that, use some kind of fancy machine learning to see whether we can map that back into the brain. And I think, as we've seen with all technological changes now recently, especially with AI and deep learning, that maybe that could give us that extra edge that we were missing. Now, this is just a big hypothesis, but definitely we're missing something like 30% here, to explain. And whether the EEG signal, which is simple enough to translate, has that capacity, that information to really diagnose something as complicated as a psychiatric disorder, we have to see. But the hope is that maybe some special techniques that use neural nets that take out the features themselves. So far, we've been engineering features ourselves, taking out the amplitude. We think this is what's really informative or not. But in fact, we've all been kind of going down the same route, connectivity or power, so on. But who knows what, in more, let's say, not intelligent, but let's say more refined pipelines will come up with, that's the hope, but we will see.
Well,
Sure.
It always starts with a patient coming to a professional for an opinion as to what's going on. And as such, the initial presentation is going to end up having to have some kind of an opinion based on the symptom presentation. So the DSM is going to live in some fashion, but it doesn't predict treatment. It basically tells the professional that they need to do some testing. And if the behavior of ADD, ADHD were to trigger an EEG, which is quantitatively processed, and an event-related potential, a visual CPT task, which you can break down with component analysis, you're going to get the same thing you get in an IVA of omission errors, commission errors, reaction time, variability, but you also get the components of the EEG that correspond with sensory detection, sensory processing, motor engagement, motor inhibition, and then self-monitoring, the last component in the list that's been identified by Yuri Krapatov's work. And the EEG basically can also then identify whether there's beta spindles, which is an outlier pattern. It's not the most common pattern in ADD, ADHD, but it requires a specific intervention. It can also identify the rare approximately 10 to 20% that have epileptiform discharges. And if your brain has an epileptiform discharge, you basically need to have some kind of a stabilizing agent or neurofeedback for stabilization, or both. But it's an unexpected finding. The doctors don't expect that your ADD is because of epileptiform discharges. They assume it's a dopamine deficiency in the striatum, so they give you methylphenidate, or their alpha's too slow, so they give you an amphetamine. If you have beta spindles, they can give you a channel blocker like guanfacine or clonidine. But there's specific matches, and the biomarkers basically allow you to match appropriate treatments with the symptom-based cluster of ADD, ADHD as the initial complaint. But very much like a cardiologist can't just send you for an angioplasty if you're complaining of chest pain, because half the people have indigestion, not a cardiac problem. You can't let the DSM behavior presentation guide your treatment, because you're going to be wrong a lot of the time. There's a lot of inappropriate angioplasties if everybody that had chest pain got one. So what we need to do is essentially listen to the story with as much empathy as we can muster, and then set the story aside and do the testing that's indicated by the story. And if you're complaining of a neurocognitive deficit of some sort, I think they can actually examine the brain, the organ that's involved with the behavior that's problematic. It only makes sense. Now, psychiatry and neurology aren't really talking to each other. If you're a psychiatrist and you want to become boarded in EEG, you have to actually go back and take a neurology residency, which is kind of crazy. You're both professionals are focused on brain function. It's just that psychiatry doesn't do as much, depth analysis of brain function. It's listen to the story and prescribe medication for clinical psychiatry generally. So, psychiatry will give you an anticonvulsant medication because other things haven't worked, and they don't have to have you having convulsions in order to give you an anticonvulsant medication. They can give it to you to help stabilize your brain function. So, but if you go to a neurologist with the EEG showing an epileptiform discharge and say, would you medicate this patient? Unless you're having a seizure, they say no. We actually have a very nice paper showing in an N of 76 cases, a psychiatric patient that has epileptiform discharges, when you give them an empirical trial on an anticonvulsant medication, 85% of their patients get better psychiatrically. It's not that they were having seizures in the first place. So the anticonvulsant didn't change their seizures because they didn't have them. But the disturbance on brain function was stabilized and their psychiatric presentation improved. And in psychiatric treatment, show me an 85% positive treatment result somewhere. Yeah, that's the lock and key, a pharmaceutical intervention that has a distinct lock and key effect psychiatrically. And again, neurology would deny that medication to those patients because, again, if you're not having a seizure, their standard of practice is to deny you that dangerous medication. When in fact, it's quite manageable. Psychiatry uses it all the time. Anyway, enough DSM bashing.
But I agree with you, Jay, that's exactly what I found once. I saw a kid who had ADHD, diagnosed with ADHD, and the psychiatrist, or I can't remember now who the doctor was, but they didn't check the brain. And when I checked it, we found interictal epileptiform discharge, which is like these little spikes, right? Mm-hmm. And that was causing the ADHD. It wasn't just a psychiatric, whatever, anyway, the line between psychiatry and neurology is shrinking, I think, anyway. But if you do see a psychiatrist, unless it's a neuropediatrician who, is specialized in checking your brain first, you will be diagnosed with psychiatric disorder, whereas you might actually have some epileptiform problems that will never be picked up upon because they do not yet dabble in these kind of brain measures. So I think slowly with time, as neuroscience becomes more and more validated, psychiatry will move into that domain. But at the moment, we're still back with the same tools from the 1970s, where you just kind of prescribing medication semi-randomly without any kind of brain information whatsoever. And that needs to change as soon as possible.
Yeah, absolutely.
Along with, well, in giving the DSM a break, Jay, maybe we can bash neuropsychology for a second. And we have a co-host that's not here today, Thomas, but Laura and I are neuropsychologists and know each other from our training. But we're using some tools of assessment that I think might have come around right after fire was discovered, or the wheel, whichever one of those was earlier. We're in between, And as we talk in conversations like this, it is promising and a little bit exciting to know that there are some things that are available, meaning they're not just in places that are funded and, universities or wherever, hospitals that have the finances to do this. You can do things like ERP, certainly QEEG, in offices like ours, and get a monumentally different data set than you do with, and I'm not going to throw any particular tests under the bus, but with the way we currently do things, you're just getting such a different data set on what's going on for this person. And I'm not saying clinical observation and experience aren't worth anything. I'm saying I can watch people do things and generate some hypotheses on what might be contributing to what they're doing. But shoot, if there's a way to know that, air quotes, right, definitively, why not cut out the middleman, right? And my biases and whatever else might be going on that day for me, right? And if we neuropsychologists can start to adopt some of these other avenues of assessment, I think, well, one, it's incredibly exciting and just kind of hopeful on our end that we'll be able to maybe just be able to delineate that much more clearer what's really going on for these folks, so we can treat what's bringing them in. Right. Yeah. So all that to say, well, I'm on board.
The question is just, there are some things that are more validated than others, like epileptiform. I think it's very well validated that that's going to have a problem with cognitive impairment. And then, and you need medication for that, or even other types of treatment. But some other things are a little bit more subtle. So this is the thing, like, it's a question of what works and what's the evidence base behind it. Now, some clinicians already have their own way of seeing, okay, this seems to work in my experience, so let's deploy it. For others, like scientifically speaking, publication-wise, the bar is much higher, so it's much more difficult to prove. Although there's a lot of papers out there that show that, for example, ADHD is associated with at least 20% epileptiform discharges sometimes. So it's a big elephant in the room that nobody's talking about, and even though it's already in the literature. So it's a little bit the case of small samples or smaller, less impactful journals publishing more, let's say, provocative, or at least provocative for the mainstream ideas that are not really picked up by the mainstream for, many different reasons, bias and so on. They don't want the paradigm to change. And it's the same thing happened with QEEG. Even though we know that a lot of these ADHD patterns are linked to, immature EEG kind of development and so on. This is not really uptaken yet by the industry. So it still takes some time to validate these, fully. But again, it's always kind of tempered by the fact that maybe not many of these signatures are 100% specific or sensitive, right? Because of this heterogeneity. So we're kind of mixed into this problem where some things work, but for some people, and then they don't work for others. So how do you square up all that as a sort of a very definitive diagnosis or prognosis? Although even without that, it's difficult to do it. It's just that, psychiatrists have selected the fact that the behaviorally that, DSM is king, although it's far from it, because, why would you sort of define somebody by just one label? It's like saying one cocktail is just the main ingredient, right? So they are new sort of directions called RDoC, research domain criteria, that are supposedly going beyond that. They're saying, okay, we should look at dimensions. So I think we'll have probably a combination of that behaviorally for interventions and as well as neurally. So, you might have one marker that is good for this child and then another one for another. And then we need to parse these markers from each other and see, okay, can we get kind of, the full spectrum? Can we explain the full spectrum? And until then, we need to be still cautious about making conclusions, right?
The psychiatrists that I've worked with have all basically come to the conclusion that they don't want to prescribe any medication before they actually look at the EEG. I worked with Camp Lejeune as a no-bid military contractor a long time ago before sequester got rid of the funding. And one of the first things they did is test to see whether we could provide any incremental benefit. I mean, why pay people to do data analysis if it's not going to benefit your clients? So we got 6 cases. The first case they sent us was a fellow who had been hearing voices, and this is a Marine, hearing voices telling him to kill people. So the psychiatrist, obviously, hearing voices, you're going to give him an antipsychotic. And they gave an antipsychotic, and the voices got worse, and they had to basically put him into the brig. We looked at his EEG, and he actually had epileptiform content, probably from one of his blast injuries. He had a bunch of them. And we stopped the examination and asked to speak to the attending nurse or physician, and said, well, you've got him on an antipsychotic. It makes the discharges that he's having worse, which is why he got worse when you started to medicate him. You have to switch him over to anticonvulsants instead of antipsychotics, because antipsychotics make the discharges worse, floridly worse. And they were afraid, first of all. Imagine you're a psychiatrist and the person's hearing voices telling them to kill people, and somebody tells you, well, take them off those antipsychotic medication. Well, you think, well, geez, what's my liability if something happens? Well, he was in the brig, so they switched him to Lamictal and away from the Seroquel, which is a sedating antipsychotic, and the voices went away. The epileptiform content was effectively treated, and the voices went away. And serendipity being what it was, of the first 6 cases, we had 3 people that had temporal lobe epilepsy discharges. The odds of that are like 1 billion to 1 or something. It's, temporal lobe epilepsy is not that damn common. But obviously the difficult clinical cases that they wanted us to consult on gave a heavy loading in temporal lobe epilepsy. But I basically have, for quite a few years now, when I used to travel to Europe to do lectures, I would walk in, Martijn Arns would set up the lectures. I would walk in and he'd hand me 6 cases I'd never seen before. And I would look at the EEG and the QEEG and tell them about the patient with no history other than the age. And at the end of that, each case, I would say, okay, whose patient was this? What did I get right? What did I get wrong? What did I miss? And after you do 6 in a row and effectively describe the neuropsychological presentation of the client, people realize that the brain is actually important with respect to their neuropsychological presence. And you can identify their symptom presentation within the EEG. And at that point, the rest of the class, to finish off the multiple day, they would be in 2 or 3 people. They'd get a list of the symptoms, and they'd have the data, and they'd have to match up the symptoms with the EEG findings. Well, they knew you could reverse engineer it blindly, but nobody does that. That's a parlor trick. It's an impressive way to show the capability, but it's just a parlor trick. Nobody does that. People that interpret EEG either have seen the patient or they get a referral with some information about the patient. So, the class basically knew that each of these symptoms had to have some biomarker associated with it, and they had to match those up. So I know it can be done. It's just not commonly being done. And I'm kind of pushing towards the go ahead and use the DSM, but at that point, do your lab testing to figure out what you're really going to do to treat the patient, because the DSM doesn't tell you how to treat.
Yeah, I think that's what's missing. Sorry, that there is not enough training in this domain, or maybe it's not, disseminated enough. The knowledge that also Jay has, maybe it's best for you to write a book as well, Jay. I don't know how many you've written so far, but somehow distill that knowledge that people can, tap into. And for those that haven't had that amount of clinical experience, how do they get onto that bandwagon? And I think probably in the future, as you said, you learned this from experience, looking at patterns, reverse engineering with the symptoms and seeing what are the connections. And then maybe, if we have enough data that's open and people can mine it, scientifically using new machine learning methods, maybe we can get to some patterns that we think are really reliable that we can actually predict. And then basically an EEG will be a standard thing that the computer will then, sort of decipher what is it that's part of the symptoms, which patterns are linked to which symptoms, and then we can treat those with neurofeedback, right?
Yeah.
But that's the goal. That's the ultimate dream that would happen. And then we can just get away from the behavior. Well, not completely, but
the neuropsychologist testing, the detailed testing, tells you basically fairly accurately what brain location isn't working.
Yeah.
Where is the problem?
Right.
But when you go there and look, it doesn't tell you what you're going to find. The EEG, you can look at the EEG and you see where the problem is and what kind of deviation it is. It's not a reversible equation. You can't go from the symptoms, which will only predict the location, and tell what's going to be happening there. But if you look at the EEG, you already know the location of the deviation because you can see it, and you know which kind of deviation it is, so you can match up the appropriate approach. So it's unfortunately not a reversible equation, because it'd be wonderful if the neuropsychology screening would end up predicting precisely how to treat. It gives you a reliable DSM cluster by telling you where the problem is, but it doesn't unfortunately tell you what pattern is there and what treatment matches with that pattern. Luckily, the EEG going in the reverse direction ends up being something that can tell you where things are wrong and kind of how to fix it, since you can see what the deviant pattern is.
Someday maybe, Jay, huh? And Thomas, someday maybe, right?
Well, the hope is that, someday, exactly, with enough data and computational kind of connections that, I think that what Jay is talking about is this sort of very sort of well-known principle in complex systems, where you try to explain a low-dimensional system, which you can say maybe behavior, it falls into a few clusters, like somebody's inattentive or not, or somebody has loss of consciousness or not. But then the network where the neural substrates that kind of generate that is the high dimensional. So you can go from high dimension to low dimension, and there's a pathway, but you cannot necessarily go in the reverse direction. We go from, sometimes you can go from low to high dimension and also predict what are the high dimension. But obviously we're working with many, many more variables in the brain, like billions of nerve cells and networks and so on, explaining something more basic as in a behavior. So we should tap into that high dimensional space as much as possible. And I hope that the EEG non-invasively has enough informative power to do that prediction. And we can only know later on with enough data. But if it doesn't, then it's going to have to be matrix style, where, we just plug in all these sensors into the brain and record from every single neuron.
Neuralink.
Exactly. Yeah. Hopefully it won't come to that.
Well,
hey, Thomas. Sorry, Jay.
Neuralink is I think a project that is having some difficulty at this point. I think they just lost one of the heads of the company as well. But they're attempting to not only allow the brain-computer interface to have the brain operating a computer, but also the computer operating the brain. And I don't know that they're going to get past their first experiment. One of the things they're trying to do is essentially take an ALS patient who's become totally paralyzed, and at that point, get him to operate a mouse, computer mouse, or XYZ, or something on the computer. Niels Birbaumer in Germany worked with ALS patients, and he had to train them when they still had some movement capability. When you can't move anymore at all, there's a learned disability. You don't even try to move. And right now, the Neuralink learning from a monkey to play Pong basically learns from the movement that the monkey's doing how to read the brain to end up operating the Pong game without actual movement. But you had to have actual movement to train the computer. So if you've got somebody who's got a learned passivity of having become totally paralyzed with ALS, Birbaumer showed that you couldn't train them with a slow cortical potential how to operate things. You had to do that when they still had some, volitional attempt. And unfortunately, I think Elon Musk's group has designed an experiment that's doomed to fail. Wait till they're totally paralyzed with learned inability, and you're not going to end up having the computer learn the patterns that they end up needing to know. Anyway, but they'll as we've said earlier today, they didn't do their homework and go back and look at what had been done before. They designed their experiment as though you could get somebody who's totally paralyzed to operate something by training them after the fact. I'm afraid they're doomed.
That's my fault. It's a toss-up between DSM and Neuralink to get Jay going. Thomas,
I'm on board too.
Thomas, you have so many publications. What are you working on next before we let you go? TomasRos.com, TomasRos.com, right?
Correct, without an H. I'm an immigrant.
Got it.
So,
aren't we all?
Yeah. So exactly, especially in the US,
Yeah. Right.
The new world.
Well, it depends.
No, I'm just working on I'm working on ADHD, obviously, but we changed track a bit. We were working with alpha a lot, and I think we're going to continue doing that. Although we tried to get funding for that for like 3 years from the Swiss Science Foundation, and they kept on moving the goalposts. In the end, we just gave up, even though we provided all the data that they wanted. Nowadays you need to submit a grant with preliminary data. So we actually did the whole experiment in the first case because they rejected it twice. But that time we had to change experiment to say, okay, well, let's do long-term now. But then in the end, they didn't want to fund that. So there's been some interesting work we've done with alpha and ADHD and PTSD that I still think is very maybe relevant to investigate, at least to cover our bases on the whole narrative of excitation inhibition ratio, because the EI balance, the excitation inhibition balance, is kind of an important marker of where your brain is at in terms of like how is it firing too much, too little. So it could have very general implications for psychiatric disorders. Transdiagnostically, like going all the way from PTSD, where the EI balance could be high, and ADHD, where it could be high or low, depending. So we use kind of alpha as a proxy for that, where high alpha power is usually an indicator of more inhibition in the brain. And so you can kind of modulate the alpha in both directions to try to tune that to this kind of optimal point of intermediate excitability. And that could have, important implications for basically cognitive performance, going from attention to anxiety and so on. But apart from that, going away from that marker, we're now starting to look at also EEG microstates, which is this kind of a specialty biomarker of the lab I'm working in at the moment, which is Professor Michel's lab. This is, in a nutshell, it's another kind of marker that looks at the spatial kind of topography of the different samples that your brain sort of the EEG visits. So you take a certain patterns of the EEG across the scalp, and you look at, which kind of cluster of spatial patterns it looks like, sample by sample. And then you can kind of cluster them into 5 or 2 up to 10, like different sort of configurations. And we know from QEEG, some of these configurations can be like frontal midline theta, then occipital alpha, then maybe diagonal configurations and so on. So this is quite validated work going back all the way to the work of Lehmann in the 70s as well. So this could have some more specificity, or at least a different kind of lens onto which one could look at EEG dynamics. And
it's an important one as well.
Yeah, exactly. And it's kind of like
microstate analysis of the default mode network, or resting state network, basically shows that there's 4 pieces of it that rapidly flip-flop between the pieces. And it looks like a stable state in an fMRI machine because of the smearing of time. But the dynamics within that network are visible in the EEG. And Roberto Pascal-Marquis did a very nice paper on that already. But every single one of the networks that's been identified within the fMRI world ends up needing to have a microstate decomposition of it to find out what's the dynamics within the network. Because ultimately there are people that are modeling the network as though they're stable states, and they're not. I mean, if you modeled the default mode network as though all 4 of the major hubs within it had to be present, you'd have a hell of a time finding that, because they're not present at the same time. They flip-flop between the pieces. Yeah. I suggest that the brain, resting state of the brain isn't a resting state. It's twiddling its thumbs. There's still activity going on. They're not doing anything necessarily terribly productive. It's an internal state, but it's not idled. And again, every single network that's fMRI identified needs to be decomposed with the microstate analysis. There's a whole career out there for a whole bunch of people.
Yeah, there's a lot of work on this new kind of sort of direction called dynamical functional connectivity, where if you take the average of all the connectivities, that's kind of static connectivity, and then you can have like different states within that within the whole resting state, about how the different regions couple together in smaller windows. And the microstate analysis is kind of similar to that. It's just not connectivity, but more like state-based in terms of the total topography. It's maybe a little bit of an older method. It assumes also that these states are kind of discrete, which I agree with Jay, they're not necessarily discrete, because there's multiple states riding on top of each other. And then basically the microstate analysis takes the winner, like the winner takes all kind of state that is. So it's kind of a cluster analysis, although of course there's multiple clusters that could be coactive. But even if you take this kind of very simple model or a simple lens onto the brain, you do find that some of these microstates can predict brain disorders, or at least, like for example, we did a study recently, which hopefully will be published. We found that this topography D seems to predict ADHD, independent of the power difference between subjects. So it's an additional marker that could be useful also for neurofeedback.
It's
like
sensitive.
An attractor that attracts states.
Yeah, it seems quite sensitive to schizophrenia.
Yeah, so schizophrenia, exactly.
Yeah.
And interestingly, we found, the paper hasn't been published yet, it's not even on preprint, but in schizophrenia, the microstate D is too short, right? And neuroleptics like antipsychotics usually will restore the sort of the value of the D to be longer compared to normalize it compared to the normal population. But what we find in ADHD is actually you have the opposite, where the state is too long. And if you think schizophrenia is that antidopaminergic drugs, right? Antipsychotics that should make it longer. And in fact, in ADHD, you take dopaminergic drugs. So one makes it longer and the other one should bring it down. So it's an interesting potential psychophysiological link, but we have to see whether that, again, my hunch is that probably, in this group of people, although we use the replication sample, we found the same thing, you're still going to get different signatures of these microstates. So you're not going to have everybody being just one microstate. You might have a a little bit more of D and a little bit less of A, and then another person would have more of B and less of D or whatever. Again, you could find subclasses, but again, you could throw maybe some normative modeling at it, like Z-score deviations for each microstate, and see, maybe turn into a neurofeedback protocol based on that.
So Pete, you can see why I think that the field has a hugely bright future. The future's so bright, I had to cover one eye, so.
You got blinded by the light.
Yeah. So.
Oh, Tomas Ros, thank you so much for coming on the show today.
It's my pleasure. It's my pleasure to chat and talk about all these issues. They're not simple. Nothing is black and white, but we're moving in the right direction, and we want to create more therapies that are non-pharmacological, that have less side effects and that have the efficacy that's required. It just requires more time to literally mine the complexity of the brain, which is apparently the most complex things in the universe. So it's not that easy. We don't even know ourselves.
And again, your website is tomasros.com with no H, TOMAS.
Yes.
ROS.com. Tons of publications on there. Tons.
There's a lot of publications, and hopefully it's not just Greek to everybody. I know that academic papers can be very, a bit kind of too many terminologies and it's difficult to know what's going on. But I also have a few videos there about trying to make it also like understandable, hopefully.
Right.
So people can try to look at those videos and see if it makes more sense from a video, with slides and explanations.
And it's not just publications by the numbers, it's look where they're published as well. Thomas gets them into major name journals. Recently, you had a consensus paper published in Brain, which is not easy to get into. You've been published in Nature publications on neuroscience. Again, it's not just the number of publications; it's where they've been published. Your academic credentials, and you're getting published in major journals, not low impact factor stuff. It's not buried in the Journal of Neurotherapy somewhere that nobody's going to read outside the field. They're published in major neuroscience journals. So congratulations on reaching out into the neuroscience world for us.
Thanks, Jay. Well, you have to kind of change the system from the inside. Although I don't believe in impact factors, but if that's what's required to make some noise, then do it. But I would hope that people would read other journals. And, if people had read a lot of other neurofeedback works that is in smaller journals, we would be on a different trajectory maybe. But unfortunately, most people don't have time and they read just the high impact journals mostly. Yeah. Right.
Well, Thomas, we're definitely bringing you back. So be looking for another invite for say 90 days. We got to have you back. It was a great show.
And you asked me to nominate somebody, right, for the next show.
Yeah. Who should we bring on?
Well, I've been thinking, and I think unless you've already had Barry Sterman, I think it's time that he gives us. Has he been on the show?
No, he has not. And it's probably a good moment to try to get him on.
Yeah.
I'm definitely going to see CJ on that one.
Or John Gruzelier, of course, my ex mentor. I'm just wondering, Barry will have many stories to tell about the past, and it's always good to get those out and we can have that.
And RIP to Joe on that.
Of course. We could have spent more time talking about alpha. We can do another session on alpha. In memoriam of Joe.
Yeah.
Alpha is my favorite sort of wave that we've been looking at so far. So there's a lot more to explore, and he definitely opened the box on that.
Yeah.
So.
And we dedicate the show to Joe Kamiya, just passed away, 95, Jay?
I believe he was 95.
Around there, yes. Hell of a life, hell of an impact on the field that we're trying to get to the masses.
Yeah.
Well, we thank everybody for listening to NeuroNoodles, Neurofeedback, and Neuropsychology podcast. The contact info for everyone will be located in the podcast notes below. Tons of Thomas's articles will be there. Please give us 5 stars on Apple Podcasts, subscribe to our YouTube channel, smash that like button on Facebook, Instagram, and please follow us on Twitter. Please give us 5 stars on Apple Podcasts. If nobody's listening, we can't help anybody. And if you really, really like us, buy us a cup of coffee on Patreon. The link will be in the bottom of the show. Cue the band.